So yeah, hi. My name is Suvaditya Mukherjee, and today I'm going to be talking about Cloud Run for the young and restless. How many of you all are students here? Please, let's by a show of hands. Perfect. How many are working professionals? That's a good number, right? So, a short introduction of who I am. Anna already did a great job at that. I'm a ML research engineer intern at Ivy. I also overlooked their GSOC program this year. Let's talk if you want to, get some insights about the Google Summer of Code program. I'm a former GDSE from the 2021 year. And I'm also an ex-SD intern at Mosaic Wellness, where I was working on MLOps pipelines. Along with that, I'm also a co-organizer for GDG MAD. So that's basically what I do. But on the off time, I am a Barcelona supporter. So this talk is going to have certain parts or flow to it. So it's important that we anchor what we are trying to do here with an agenda. So first off, we have compute offerings on GCP. This talk is going to focus on the different components that make up Cloud Run, and then we will be exploring why you should prefer Cloud Run over any other services which provide similar features. Before we dive in, it's important to keep things in perspective. This perspective is, well, quite literally just that. Every cloud is basically just someone else's computer. That's all you're doing. So it's important to keep that in perspective before moving on. First off, we have Compute Engine. Compute Engine allows you to use highly configurable virtual machines which can be suited to your requirements. This can be something along the lines of very basic virtual machines that you're spawning up just to, do your homework, to something like confidential computing, where you can secure your workloads very easily within configurable options. Next, we have Kubernetes Engine. How many of you all have touched Kubernetes before? That is a smallish number, but anyway. How many of you all have touched Docker before? That's a good number now. Now, I want you all to understand it this way. You all have used Docker before, but imagine that if you could deploy containers at scale very quickly. On a very basic scale, I'm trying to explain Kubernetes here. If you could control the orchestration of several containers together, that is what you would use, Kubernetes. So Google Kubernetes Engine allows you to develop Kubernetes native applications, and also along with that gives you complete control over the choice of machines that you want to use. If you want a fully managed solution wherein you don't need to worry about any scaling, you don't need to worry about what computer, what processor, what RAM your service or application uses, you can use something called GKE Autopilot. That will allow you to configure very easily. But on the other hand, if you want full ingrained control over your application, you need to use GKE with Anthos. Next, Cloud Run. I will not spoil that one. That's just a placeholder. But I want you to notice one thing. There is no section name on top of that. You can see that Compute Engine and Kubernetes Engine come under IaaS. Anyone with the full form of IaaS? That's a lot of answers. That's again a lot of answers. It's infrastructure as a service that many of you all pointed out. Anyone about PaaS? Perfect. So IaaS and PaaS, that's how you can define different services. But it's important to understand that Cloud Run does not directly fall under any of these. It falls under amalgamation of all these different categories. Finally, Cloud Functions. Cloud Functions allow you to deploy independent applications or independent functions onto Google Cloud, where you do not need to worry anything about what kind of engine or what kind of compute backends your application is using. Does anyone know what that means? What compute without worrying about what the configuration is mean? In very simple terms, if you have a server, and you do not know what configuration it is, but you know that you can run applications on it. You don't need to worry about what the server is about. Any guesses on what I'm trying to refer to? Serverless, absolutely. Cloud functions are one of the most important examples of serverless mechanisms on Google Cloud. Finally, now we have a high-level overview of what the compute offerings on GCP are. Next, we look at containers. How many of you all have touched upon containers before? That is a small number for people who worked with Docker. So anyway, so we'll be exploring what containers mean. Well, on a very basic scale, containers are portable units of software which allow you to execute in an isolated environment and encapsulate all your dependencies. You don't need to worry about, okay, how many of you all know about deep learning libraries like TensorFlow, PyTorch, and so on? Do you all know that all of them use CUDA? Have you all heard of CUDA? Okay, by the way, let's keep the session interactive. You all can reply with a yes or no as well. That's fine. You don't need to, just raise hands. So have you all interacted or used CUDA before? Somehow. Perfect. So have you all experienced the struggle that comes with setting up the drivers of CUDA? Exactly. So what you can do instead is run CUDA in a container. With that, you don't need to worry again and again about different drivers, different versions, CUDA, CUDNN, everything. You don't need to worry about all that. You just start work. The biggest advantage of containers, any language, any binary, any dependency. You don't need to worry about what kind of tech is within the container as long as you can run it directly. That is pretty much the principle behind Docker containers, or any containers for that matter. You say that it works on my machine, so you just export the entire machine altogether. That's Docker containers for you. But why use containers? Of course, we just talked about how it makes your life simpler, but another very important aspect of it is that it is reproducible. You can easily scale the containers. You can easily make changes and you can easily scale them in different manner. You can scale it horizontally as well as vertically, but most important application is doing it horizontally. Downstream use with Kubernetes and Docker Swarm. Now, Docker Swarm is somewhat discontinued, but yeah, you can use it with Kubernetes. These containers are directly linked. Finally, minimal overhead. One might think that wrapping some kind of software code with different kinds of drivers and so on will somewhat slow down your code, will somewhat affect the performance of your application, but that is not the case when it comes to Docker engine or Docker containers for that matter. Finally, deploy in multiple hosts. Imagine you have a container image. You have your container with you. You can practically put that container anywhere you want, and you can literally just do Control-C, Control-V every damn time. You don't need to worry again and again. But the process of scaling is not a Control-C, Control-V operation, let's be clear on that. But with all of this information, you might think, how is it any different from a virtual machine? How many of you all have come across that question? Why is a Docker container any different from a virtual machine? Anyone? Anyone think about that? A no is a fine answer, by the way. All right. Well, on a very simple scale, virtual machines directly interact with the software, the OS that you're working on, and it will allow you to make machines with a different OS on top of the original OS. But what you see with the Docker, Docker runs its Docker engine on top of the original OS, which allows you to deploy different containers with different sizes and different services at the same time. This allows you to utilize your hardware in a much better way. Having covered containers and what the offerings are, we now look at the serverless model. Serverless came out of necessity. It came out of evolution of applications where, we had physical servers, then we came across virtualization, then some cloud compute, then we had containers, and finally we are at the last iteration of serverless. We don't know what's going to come ahead. The serverless model is basically just hands-free. It's like Bluetooth. You don't need to worry once you're done configuring it, correct? So, oh, my bad. Sorry, yeah. Well, first off, it's a fully managed solution. You don't need to worry about what kind of configurations go underneath it. There is no need to manage the servers anymore because the underlying infrastructure is handled by Google services. It allocates the compute on its own, and well, on a very simple scale, serverless is a function as a service. First off, most important pros that come under serverless is it's a very good way to save costs. You can reduce your cost because you don't need to worry about keeping the server on all the time, because the server executes the requests every time by making changes or by spawning a service request. It spawns the virtual machine on its own, it fulfills the request, and then it will shut it down on its own. So you don't need to worry about keeping the server on all the time. It's highly scalable because it can provide all infra provisioning at the same time. You don't need to, again, there's a lot of things that you don't need to worry when it comes to serverless. And reduced operational overheads. But not everything is as perfect as it may sound. Cons are also present. First off, it's very challenging to debug. Simply because every time there is a problem in your software, the logs come at a delayed notice. They don't come instantly as you might see in normal applications. They come onto other services like Logger or other Logcat services and so on. Cold starts have a high latency. Serverless depends on the concept of cold starts, wherein every time a request is made, it will try to spawn a new container or a new compute service, and then it will fulfill your request. That causes latency. Finally, no direct control over the underlying infrastructure. Because everything is fully managed, you don't have any control over what's happening and what kind of compute is being used. That was a very short cover of how serverless and containers work. Because now what we're going to see is trying to understand why or when we should use servers over traditional, when we should use serverless over traditional servers. But again, we need to keep perspective about quite a few things. First off, we should remember that serverless is basically just servers again, but they have some kind of control on top present over there, right? So it's important to keep that in perspective as well. Now I want interaction from you all, wherein I want you all to answer questions. I want you all to answer what we will use. The two options are servers and serverless. Let's say that we have an event-driven application. It has functions that execute on specific triggers. You need to do a certain action in order to cause the function to execute. And there's no centralized control structure. They all work independently of each other. So what do you think should be used here? Serverless. Yeah, absolutely. That's what you use. Because serverless allows you to directly make use of different kinds of compute as per your requirement, and it independently manages all of those services together. Long-running applications. What do you do in that case? I didn't give all the conditions yet. They are long-running applications, but resource usage can be predicted. Then you have persistent connections and demand for low latency. I think the last point basically gives it away, wherein you need to use servers. Finally, high-performance computing, where you have predictable heavy resource usage, low resiliency, high risk, and complex processes. What do you do in that case? Servers? That's right, absolutely. Servers is what you use when it comes to high-performance computing. Finally, that's a microservice architecture diagram. The services are independent of each other. They are broken down into functions. And that's pretty much a giveaway. What do you think we should use in this case? Serverless, absolutely. So, do you recognize any patterns that comes out of this about when we use servers and when we use serverless? Perfect. So we basically understand that when it comes to stateless HTTP, we can use Cloud Run or its derivatives. But when it comes to more traditional applications, we can shift to Cloud Functions or Cloud or Firebase or other Google Cloud applications. Now finally, we come to Cloud Run. Well, first off, we talked about containers and we talked about serverless. Cloud Run is an amalgamation of the two. You can run containers serverlessly. It's completely managed with auto-scaling and inbuilt redundancy and security, so that you don't need to worry about any kind of cyber attacks or any kind of problems when it comes to your load not being fulfilled in the right manner. Finally, a very important thing when it comes to Cloud Run is that it does support WebSockets, gRPC, and HTTP too. So you don't need to, again, look towards server options simply because Cloud Run does handle that for you. How does Cloud Run work? This becomes something which relates to Kubernetes because Cloud Run works on the concept of Knative. By any chance, have any of you come across Knative? That's one person. All right. So basically what happens in this is, each of the revisions that you see on screen right there, each of them is a certain service. Each of them is a certain application, right? When you make changes to your application, each of them creates a new revision. Every time you hit an endpoint that is linked to a Cloud Run function, that will spawn a container within Google's infrastructure, fulfill your request, and shut down the container, all for you. Finally, why Cloud Run? Why use Cloud Run over maybe something like Cloud Functions or maybe Compute Engine or the other compute options that we saw? First off, scalable. Extremely scalable and easy to use. Secondly, you can use direct containers instead of worrying about dependencies. You don't need to worry about whether the application has a certain package, whether Java works, whether some other language works. You don't need to worry about that. You can just literally directly link your container image and that's all you need to do. Interoperability with other Google services like Cloud Build, Artifact Registry, Cloud Code, Secret Manager, everything. And lastly, you only pay for what you use. You don't need to think about continuous resource utilization and then the $10,000 bill that comes to your email. Finally, some interesting examples of where Cloud Run is used in practice. How many of you all have come across the company Carrefour? That's 2 people. Anyone else? That's 4 people. Okay. Anyway, so Carrefour is a company which is mainly based out of France. Now, since they are based in France, they somewhat have a primitive way of looking at things, and then they have their server architecture present in France. They don't have server architecture at the location where they are serving. Similar goes with Carrefour Taiwan. They had their servers in France, but the people who were using it were in Taiwan, which caused a very high latency in their applications. Hence, what they did was shift to a Cloud Run architecture, which was built on top of very interesting microservices. Something that you can also look up on Google Cloud's official documentation as well. Since Cloud Run was distributed, now the servers were not in France. The latency did not depend on the distance between France and Taiwan, but it was being shifted to the data centers of Google at Taiwan. Before, on-premises servers at Carrefour, with support from a third-party data center in Hong Kong, but it wasn't helping way too much. Finally, they changed to a Google Cloud Run-based architecture wherein they could very easily scale with their requirements. How many have come across L'Oreal? I think quite a few must have. Yeah? L'Oreal, right. So with L'Oreal, the idea was a bit different. L'Oreal was trying to use Cloud Run in a data analysis platform architecture, wherein basically they got all the information from the phones and desktops where their application and website was running on the user's devices. They got information from the devices, they processed that information using EventArc, and then they performed their different transformations, the ETL pipeline, through Cloud Run. They orchestrated it through Cloud Run. In that entire pipeline, we had other things as well, like cloud workflows, BigQuery, and others, but the main essence of it was Cloud Run. Finally, we're going to come across a demo that I'm going to show you. I am more of a ML person, as I had explained before. So I'm going to show how you can deploy a machine learning application on Cloud Run. What this is going to demonstrate is not only the fact that you can deploy something as finicky as APIs, but also the fact that high compute options are also available on Cloud Run, which allows you to execute something as demanding as a machine learning model on Cloud Run. Right, so what you see here is a very simple repository where I have hosted some machine learning code. How many of y'all are TensorFlow users here? That is a decent number again, but anyway. How many of y'all have used APIs before? Ali's doing his work, that's nice. So what we're trying to do here is take a machine learning model and make a API that will be used to serve image classification results, right? If you all have any questions about this code, please feel free to ask the questions during the question session. Basically, what we're trying to do here is define two endpoints, one being the health check, which will allow us to just check whether the app is up and running. And we have a perform inference function, which allows you to basically just run inference on the image that you enter, correct? So we go to Cloud Run. And we create a service. Basically, this will also allow you to deploy direct revisions from a source repository. For example, here in GitHub, I could make direct changes to the code, and I won't have to worry about going into Google Cloud again and redeploying my application. All that I need to do is sit and wait and watch. Just pushing these changes to GitHub will trigger changes on Google Cloud, which will in turn build the application again, push it to artifact registry, and deploy the application. So we do a continuous deploy. We set up the repositories. What we just did here is choose the repository and basically put a build configuration in place. Now the application that I have has a very simple Docker file, which basically just calls the API. It's a Flask API, so it just does Flask run app, right? That's all. So that is what's happening in the Docker file. And the main regex that you see here is basically just going to check what branches are available on cloud, on the main repository, and hence build only if there are changes on those specific branches. For example, here it's main, so any branch with the satisfying regex will be built. We save that. Here you can choose options for auto scaling. In auto scaling, you decide how many instances you want to keep running or how many maximum instances you want to start when your application is running. For example, if I keep it 0 here and maybe 10 instances here, that should work out fine. We also allow direct access from the internet, but if you're building for an internal company application, you could choose to make it internal, wherein it would depend on the virtual private cloud that you may have in Google Cloud Service. Finally, authentication. If you have strict requirements for security, you can use Cloud IAM and authenticate every request. But if you don't want to do all of that, you can just simply keep it allow unauthenticated invocations, and that will allow you to call the API from anywhere you want. Here we can make changes to the containers settings, all the different kinds of services that are present within the container. We can choose the container port and the RAM and the CPU. This will allow us to, this gives us a little bit of control over the configuration of the containers. We can probably set this to maybe 1 GB. Execution environments can stay as they are. And finally, we just click create. This is it. This is all we need to do to have a practical cloud run service running. Continuous deployment is being created, and you can also track the progress of your build on cloud build with the logs here. Basically, what is happening here is a 3-step process wherein first the application is built, all the packages are downloaded onto the main engine and they are built, following which the image is pushed onto artifact registry, and finally the revision is deployed wherein it will be available for use through Cloud Run service. Another important thing to note about the Cloud Run program is the fact that you have a lot of observability built into the system. So you can talk about metrics, you can talk about SLOs, you can talk about the logs that come, you can talk about networking security, networking changes, you can track latency of your application, maybe how many milliseconds it takes for your application to work, and so on. You can make those changes on demand. And if you want a very custom solution, you can even just go and change the YAML on your own.
When using Cloud Run to run ML applications, won't that make the cold start and the response time much higher?
Good question. Yes. But it will again depend on the kind of configuration your Cloud Run service is built on. If you have GPU enabled ones, that shouldn't be too difficult. But if you use a CPU one, as I'm showing right now, you might see that there is some latency that is caused. So yeah, your concern is valid. It does have that problem.
Thank you.
But the latency is basically just not about the actual processing of the machine learning model. It's the latency of that plus the cold start. So both of them get added up. Within execution details, you can again see a lot of observable statistics. You can get all the different kinds of notes about how your application service is defined. Have you all used Gunicon before in your applications? Gunicon versus Flask. Anyone? That's one person. Anyone else who's used Gunicon before? No? So when you have an application like this, you can try to deploy it on different threads. Sorry, that's the requirements file. Yeah, there you go. So instead of just doing a simple Flask run app.py, you could also use Gunicon, which will allow you to start a multi-worker environment and basically parallelize your application, but at the expense of more requirement for your compute. Here I've just set workers equal to 1, which makes it equivalent to a simple Flask app, but it is easily changeable. So you can just set the worker number to a higher digit, maybe 4 or 10, something like that, and it should scale along the line. So if you see the request that I'm trying to make here, you'd see that the first part is a URL that Cloud Run will provide on its own, that you can extract from the main page right here, the URL. This you put into Postman and then hit the endpoint that you want to use. So here, for example, the endpoint that is named is inference. So inference is what you hit. You set the body, and in the body you send the image. The image is of a cheeseburger that we are going to send in. And okay, the deploy is not complete yet. Perfect, the revision is being created. Okay, deploy is complete, and we are now going to see a huge green tick coming up right here. That will basically signify that your build is complete and your application is ready for use, correct? So we go here, we set up everything, and we do a run send. So you see the sending request is taking a bit of time because now it's creating the container instance and then it will run your request. It will run the processing to serve your request. You see that the model gives 5 recognitions: bagels, bananas, cheeseburgers, corn, and face powder for some reason. But you see that cheeseburgers have the highest value. If I don't know if I can zoom in there. Can I? Oh, I can't. Yeah, so what you see here is basically the confidence score that the model returns. It says that the image that I showed it was a cheeseburger, right? Going back to my slide, I'm going to show you what that image looked like. I did have some images, but yeah. So if you're looking at what we just did, it was basically a CI/CD pipeline that we just created. The developer can push code to source control like GitHub. That will trigger a build on cloud build, push that image that was built onto container registry, and then pull that from cloud container registry to Cloud Run. Here, container registry or artifact registry, either one. So we push to GitHub, we deploy to Cloud Run. That's the burger that we used, right? That's the cheeseburger that we fed into the model, and we got a result out of it. You can see that the last time I ran it, it did give the same results: bagel, banana, cheeseburger, corn, and face powder. So yeah, that is basically all the steps that we have now covered to see how Cloud Run is useful for someone that is developing solutions iteratively and quickly. Yeah, that is all the steps that we have covered. Feel free to just maybe take a look back and understand what kind of different choices we have made during this application. Finally, any ending questions that you may have? Yes.
So is the model trained on every request, or is the trained model saved in some pickle
Trained
file?
model is saved. Trained model is saved. Actually, in the application that I've built, it's quite literally a pre-trained Keras model that is being used. It's a very simple application.
So is it dumped to a pickle file or something?
No, it's not on a pickle file. It's actually stored on Google server somewhere else, and it's basically just directly downloaded.
Okay.
But if you had something like that, if you had probably a pickle file or something of that sort, it would be encoded on your image, or you can pull it from a GCS bucket or something of that sort. All of those options are available with the Google Cloud Python SDK or any other software development kit you're using.
Okay, thank you.
Yeah. Anyone else? Got it. So, yeah, thank you so much. That is my time.